imagine for a moment if we could tap into the weird, powerful world of quantum mechanics, but without needing to freeze everything down to, well, practically absolute zero.
Right. For decades, that's been the assumption, hasn't it? Quantum effects need extreme cold.
Exactly. It's been a foundational rule. But what if that rule was about to be, profoundly broken?
It's a fascinating question, and it looks like we might actually be seeing that happen now. The traditional view is so tightly coupled with cryogenic cooling.
Uh-huh. And this breakthrough really challenges that.
It really does.
So this deep dive is all about a groundbreaking study just published in Nature Physics by researchers at ETH Zurich. They've done something pretty remarkable.
Putting a relatively large object into a high-purity quantum state at room temperature.
Right, at room temperature. That phrase alone should make people sit up and take notice.
And when we say relatively large, we need to be clear. From a quantum physicist's point of view, this thing is, well, it's enormous, not just a few atoms.
Good point. So we're drawing from their paper, High Purity Quantum Optomechanics at Room Temperature, and also a really helpful piece from ETH Zurich called Pure Quantum State Without the Need for Cooling.
Very appropriately titled.
Indeed. So our mission today, let's unpack what high purity quantum optomechanics at room temperature actually means, in simple terms.
Yeah, let's explore why it's such a big deal, why it's a major breakthrough.
And look at the exciting potential benefits, the applications this could unlock for you listening and for the future of technology. Okay, let's get into it.
So the why behind this is really about pushing back against decades of scientific convention, like you said. For the longest time, getting those really pure quantum states, it meant unbelievable effort.
Right, we're talking costly, complex setups.
Hugely energy-intensive cryogenic cooling. Temperatures, just fractions of a degree above absolute zero, minus 273 Celsius.
Which is just incredibly cold, hard to even imagine, like a giant, super expensive freezer.
Exactly. And that need for extreme cold has been a massive barrier, hasn't it? It keeps quantum tech confined to specialized labs.
Absolutely. But here's the core finding from ETH Zurich, and it's a bit of a jaw-dropper.
Go on.
They managed to cool a specific motion, a megahertz frequency librational mode of a tiny levitated silica nanoparticle down to its quantum ground state.
Okay.
At room temperature, no giant freezers.
That is the key. Room temperature.
Yeah. And the purity they achieved, it's kind of stunning.
It really is. They reported a phonon population of just 0.04 quanta.
Okay, break that down. Phonons are like tiny packets of vibration, right?
Essentially, yes. The particle's internal wiggles are energy packets. Fewer phonons means a purer, more quantum state. So 0.04 quanta. That means, on average, there's barely any vibrational energy left.
How pure does that translate to?
An astounding 92% state purity. Think of it like having a perfectly still pond versus one rippling with noise. This is a very still pond.
And this purity level, achieved at room temperature,
Yeah.
how does it compare?
This is where it gets really interesting. It actually exceeds what's often achieved with mechanically clamped oscillators that are cooled cryogenically.
Wait, really? Better than systems in super freezers?
Yes. And it even surpasses the performance of some gigahertz frequency oscillators when they are laser-cooled in cryogenic conditions.
Wow, so the old rule, colder is pure, isn't the whole story then?
It seems not.
Oh.
It suggests maybe how you isolate something, how precisely you control its interactions, might be even more crucial than just raw temperature.
Which puts these levitated librators right at the forefront.
Absolutely. At the forefront of room temperature quantum optomechanics.
Connecting this back, it makes quantum tech potentially much more efficient, more accessible.
Exactly. The researchers used a great analogy.
Yeah.
They said, it's like we've built a new vehicle that transports more cargo than traditional trucks, and at the same time consumes less fuel.
That says it all, really. Efficiency and capability without the huge energy cost of cooling.
It's a fundamental shift.
Now, you mentioned this relatively large object being enormous for a quantum physicist. Let's clarify the scale again.
Sure. We're talking a cluster of silicon nanospheres. Overall diameter, maybe 1,000th of a millimeter.
So about 10 times smaller than a human hair? Still tiny for us.
Tiny for us, yes. But think about it. That object contains several 100 million atoms. In the quantum world, that's practically macroscopic.
Right. And why is dealing with a larger object like that such a hurdle for quantum states?
Ah, good question. Larger objects just have so many more ways to interact with their environment. They get constantly jiggled by air molecules, even tiny vibrations.
More thermal noise, more classical motion, basically.
Precisely. Which makes it incredibly hard to isolate them and see the delicate quantum effects without serious cooling. The fact they could do this for something with hundreds of millions of atoms
And detect its tiny quantum movements so precisely.
is a genuine first. Nobody's managed that level of precision for an object this size before. It pushes the boundaries.
Okay, so given those challenges, how on earth did they pull it off? It sounds incredibly difficult.
It starts with a technique called optical levitation, using an optical tweezer.
Like tractor beams in sci-fi.
Huh. Sort of, yeah. It's a focused, polarized laser beam that traps a single nanoparticle in a vacuum chamber. The light holds it in place.
So no physical contact, eliminating vibrations from a surface.
Exactly. It gets rid of gravity's pull, gets it away from contact noise. That isolation is step one.
But you said it's not perfectly still even when trapped. You mentioned libration. What is that?
Right. Libration isn't the particle moving around. It's a tiny, super fast, very weak rotational wobble.
A wobble.
Yeah, think of a compass needle settling. It quivers a bit first, like that, but much, much faster and smaller. This particle makes about 1 million tiny deflections every second.
1 million per second. Wow. And each one is tiny.
Just a few thousandths of a degree. Unbelievably subtle.
Okay, so what does this have to do with the quantum ground state and this 0-point fluctuation idea? You hear that nothing can be perfectly still in quantum mechanics, right?
That's exactly it. That tiny, constant rotational trembling is a manifestation of fundamental quantum motion. It's the 0-point fluctuation.
Even at absolute zero, there's still this inherent quantum jitter.
Precisely. Quantum mechanics dictates there's an irreducible uncertainty, a minimum amount of movement. So the goal here was to get rid of all the other jiggling, the thermal noise, the classical stuff.
To isolate and see just that fundamental quantum movement.
Yes. To reach the ground state where only that 0-point motion remains. Like trying to hear a pin drop in a silent room.
Makes sense. So they isolate it with light tweezers. How do they actually cool away the extra room temperature jiggling without cryogenics? What's the trick there?
The cooling mechanism. It's clever. They use light again, a technique often called optical sideband cooling. They couple the nanoparticle to a special light trap. Yeah, a high-finesse optical cavity. Think of it like a hall of mirrors for laser light. The light bounces back and forth thousands, maybe hundreds of thousands of times.
Okay, intensifying the light's interaction with the particle inside.
Exactly. And as the particle vibrates, it wiggles, it interacts with this intense light through something called coherent scattering.
Coherent scattering.
Basically, they enhance a specific process called anti-Stokes scattering. Imagine light particles, photons, hitting the wiggling nanoparticle.
Okay.
In this process, a photon hits the particle, absorbs some of the particle's wiggle energy, its heat, and then leaves carrying that extra energy away.
So the light carries away the heat?
Effectively, yes. It transfers energy from the particle's motion into the light field, which then escapes the cavity. It's like using light as a tiny vacuum cleaner for vibrational energy.
That is ingenious. Using light to cool something down to its quantum ground state.
It's incredibly precise.
But the source's stress, that battling noise, was crucial. What kind of noise was the main enemy here?
Right. Noise is always the challenge. They dealt with thermal noise using the levitation and vacuum. But the really critical one was laser phase noise.
Not just random static, but noise from the laser itself.
Exactly. Tiny fluctuations in the laser light's wave pattern. This kind of noise has limited similar experiments before because it just drowns out the quantum signal you're trying to see.
So how did they beat that laser noise?
This was a key part of their success. They implemented an active phase noise cancellation system.
What does that do?
They actually call it a phase noise eater in the paper.
Ah, I like that.
Me too. Yeah. It essentially detects unwanted phase wiggles in the laser light in real time and then generates an opposite signal to cancel them out.
Like noise-canceling headphones, but for a laser beam.
That's a perfect analogy. And it worked incredibly well. Reduced the noise by up to around 20 decibel.
Which is a huge reduction.
Massive. And that allowed them to reach a point where the main limitation wasn't environmental noise anymore, but something called quantum back action.
Ah, quantum back action. That's the unavoidable disturbance you cause just by measuring a quantum system, isn't it?
Exactly right. It's the fundamental limit imposed by quantum mechanics itself. They basically got rid of almost all the external noise and are now bumping up against the laws of physics.
That's incredible. They've refined it that much, even at room temperature.
It really shows the power of the technique.
So this feels like it could really open the floodgates for quantum tech, making it more practical. What's next? What are the exciting applications here?
Oh, the possibilities are really exciting, especially in quantum sensing.
Like detecting really, really tiny things.
Exactly. Super sensitive sensors for tiny forces, displacements, maybe magnetic fields. Think about searching for dark matter.
Dark matter. How?
Well, potentially by trying to measure the minuscule force that hypothetical dark matter particles might exert on the sensor. Because the system is so pure, so isolated, it might pick up signals lost in the noise before.
That's genuinely mind-blowing. What about more down-to-earth applications?
Well, think about medical imaging. Maybe detecting really weak biological signals currently hidden by background noise. New insights into cells, maybe diseases,
Interesting.
and navigation, especially where GPS doesn't reach, like underwater or deep space. These could lead to hyper-accurate motion sensors.
So autonomous vehicles, submarines, probes could navigate with extreme precision for long periods.
That's the potential, yes. A big deal for future tech.
And what about fundamental physics itself? What new questions can we ask?
This opens up whole new ways to test quantum mechanics at scales we couldn't reach before these larger, yet still quantum objects.
Pushing the boundaries between the quantum and classical worlds.
Exactly. And investigating that deep mystery. The relationship between gravity and quantum mechanics. How do they fit together? This platform could offer clues.
And maybe even probe weird quantum states like superposition for larger objects.
Potentially, yes.
Mm.
Macroscopic quantum superpositions, an object being in two states, maybe even two places at once. That's a major area of research this could impact.
Wow. So it's not just about building things, it's about understanding reality itself. Are there plans beyond just cooling these states? Can they manipulate them now?
That's the next frontier. Achieving this high-purity ground state is the crucial first step. Now they can think about preparing more exotic, non-classical states,
Like what?
like squeezing the quantum state,
Right.
reducing uncertainty in one aspect, like position, at the expense of increasing it in another, like momentum. That's key for ultra-sensitive measurements.
And you mentioned effects unique to rotation.
Yes. Things with cool names like orientational quantum revivals or quantum persistent tennis racket flips. These are complex quantum phenomena specific to rotating objects that they can now hope to explore.
Sounds complex.
It is, but it opens up new physics. Plus, the frequency they achieved means they could potentially link these nanoparticles to other quantum systems.
Like trapped ions or superconducting circuits.
Exactly. Creating hybrid quantum systems, combining the strengths of different approaches, building a sort of quantum network.
That sounds incredibly powerful. And wrapping back to the practical side, the big advantage is avoiding the cryogenics, right?
That's the game changer. The system is described as relatively simple, cost-effective, and crucially, it avoids all that time-consuming, energy-guzzling cooling.
Which dramatically lowers the barrier for entry.
Hugely. It makes quantum technology potentially much more widespread. And importantly, miniaturization seems possible, at least in principle, for many of these applications.
So maybe not just lab experiments, but actual deployable devices down the line.
That's the hope. The path looks much clearer now.
So recapping, what we've explored today is really a major leap, achieving these high-purity quantum states for relatively large objects at room temperature. It's not just possible, it's been done.
And it fundamentally challenges those long-held assumptions about needing extreme cold.
Right. It reinforces that quantum mechanics isn't just for the super cold labs anymore. It's becoming more accessible.
Poised to impact our lives in ways we're probably only just starting to grasp, from fundamental science to maybe even medical tech.
Which leaves us with a really provocative thought, doesn't it? If we can now control these delicate quantum states in larger objects without extreme cold, what else might be possible?
What previously unimaginable quantum technologies, maybe things beyond even sensing, are now within reach.
And maybe more profoundly, what new questions about reality itself can we now ask, freed from the constraints of those giant freezers?